little bit, I guess, 5 minutes late, but that's okay. All right, so Newton's method is what we call a numerical method for solving equations. Suppose you want to solve an equation. Suppose you want to solve an equation like, hey, where does e to the x equal x squared? I mean, if you pull up Desmos, they certainly cross each other once over here. You know, e to the x and x squared cross each other once there. And maybe somewhere else. Nope, looks like not anywhere else. Yeah, let's do it. Let's add a +1 in there, actually. Or plus, is that what I want to do? It's like a +3 or something like that. Yeah, where does that happen? Looks like they're going to cross once. Okay, where is that? It looks like it's going to be somewhere around -0.7, but like not exactly. You know, there's -0.7. It's going to be a little bit to the left of that. I mean, it's not obvious at all what that is. Probably some irrational number, knowing e to the x. But how would you go about solving that? I mean, you can square root both sides, and then you have e to the x, square root of e to the x equals x, but that doesn't kind of solving it, right? Because like you didn't isolate x because you got an x on both sides of the equations. That doesn't count as solving or anything. You can do a log of both sides. E is the natural log of x squared. That sort of thing. Okay. Is that what I meant to do? Oh no, that's not what it would look like. It would be x is the natural log of x squared. Okay, and then okay, x is 2 times the natural log of x. But now how do I solve for x? I've still got an x in there and an x over there, right? Well, dang, how do we solve it? Problem is that algebra cannot solve this equation. This is what's called a transcendental equation. Transcendental equation. Or an example of one. It is a transcendental equation, not the transcendental equation. Don't get confused. It can't be solved by algebra. But if you want to figure out the solution of an equation like this, Desmos is still able to tell me what it is. Right? -0.703, approximately. It's rounding to 3 decimal places, right? So how is Desmos able to do this? If you can't solve this equation with algebra, like literally cannot, not just like I haven't taught you how to do it yet, but like there is no way to solve this equation with algebra. How does Desmos get the answer? The answer to this question is that what Desmos is doing is applying what's called a numerical method to solve the equation, which means that it's basically working with numbers, right? Like actual like decimal form numbers, right? And it is applying some sort of algorithm to get an approximation for the solution to this equation. It's not actually able to compute an exact solution. It's trying to find an approximate solution. So, there's lots of different numerical methods. Newton's method is just one of them, but it's one of the simplest, and it's easy to learn. It's easy to like grasp based on just the information that just what you guys have learned. Okay. So here's the first step. The first step in Newton's method is to rearrange the equation. Rearrange the equation to the form some function equals 0. Okay. So you can always do this with an equation, because you can always just subtract things from both sides until you have 0 on one side. So subtract everything from the right side, move it all over to the left side, and now we have a function equals 0. So our function f of x is e to the x minus x squared. Okay. Now, that is the format that you need to put your equation in order to apply Newton's method. Because while I'm presenting Newton's method as a strategy to solve an equation, really what it is it's a strategy, it's a technique to approximate the 0 of a function. A 0 of a function. That's what it really does. It's just that finding the 0 of a function is the same as solving an equation. Okay, because of this idea that you can just put everything over on the left side, set it equal to 0, and then it's like, that's your function. Let's figure out where it's equal to 0, right? So finding zeros of functions and finding solutions to equations, same thing. All right, so now we have a function to work with. Let's kind of step back and talk about in general, let's actually go ahead and do it. Let's get rid of that and do a minus x squared here. There we go. It looks something like that. Okay, so sure, we can draw that. In fact, actually, instead of drawing it, I'll just snap it and put it in the notes. Okay, there is our thing. We want to figure out where that 0 is. Okay, well, here's what you do. You start with a guess. We're going to call that guess guess 0. It's an initial guess. Okay. And it doesn't even necessarily have to be that close. Let's say guess 0 equals 0. I mean, it's not even that close. It's a pretty bad guess, right? It's obviously not 0. 0 is here, and the function's up there. It's something negative, but it doesn't really matter. For our purposes, we'll just say the guess is 0. So what we are going to do is look at 0 here. Here's our first guess, G0. And there is the point on the graph. It's not on the x-axis, so this is clearly not the answer we're looking for. But what we can do is we can compute the linearization of the function at that point. Oopsies. We're going to compute the linearization at that point right there. And I'm just going to put a come on. Just going to put a tangent line right there. There we go. Yeah. Like that. There's a nice little tangent line. And we can compute that linearization. And then what we're going to do is figure out where the linearization crosses the x-axis. Where's that tangent line cross the x-axis? That's going to be our next guess, which we'll call G1. Okay. Hypothetically, if you take your initial guess, look at the point on the graph, make a tangent line, and look at where that tangent line crosses the x-axis, that point should be closer to the correct answer than your initial guess, hypothetically. We'll kind of address when it is or isn't true later on, but you can see that the distance, it is closer, right? It is slightly closer. So that should be an improvement. Okay. So how do we do that? Well, what we do is we say we want to make our find a linearization at G0. So we're going to need to know the derivative of the function. Okay, our function is e to the x minus x squared, so it's going to be e to the x minus 2x. We're going to need to know what that is evaluated at our initial guess. So that's at g0, which is, we said g0 was just going to be 0 here. So f prime of 0 is e to the 0 minus 2 times 0. This is equal to 1. We also are going to need to know f of 0. So, you know, our initial point is like 0, and f of that point is going to be e to the 0 minus 0 squared, which is also equal to 1. So what we have is our linearization number 0 is the y coordinate 1 plus the slope, which is 1, times x minus 0. In other words, just 1 plus x. Nice. 1 plus x. Okay. So then we would figure out, where does this equal 0? 1 plus x equals 0. X equals -1. And that is our next guess. So this is what we're doing in this step here is solve. I guess we're finding the x-intercept of the linearization, and then set the next guess equal to that. So we're going to do g0 or g1 equals -1. So I didn't draw my tangent line perfectly well. This is supposed to be slightly over here. This is supposed to be like there instead of there. Whatever. That's okay. And then what we do is we repeat. We go back to step 2, and we're going to repeat it. We're going to loop. Okay. For those of you who are computer science majors, this is an algorithm, so it has a loop in it. It's like you just take the previous output and plug it back into the loop and then run it again, you know? And so it's like, it's going to take this guess value and it's going to keep updating the value of the guess. The fact that this is like similar to other algorithms, you know, and like concepts that you study in computer science means that this method lends itself to programming. And so tomorrow we're going to write a program to perform Newton's method in Python. But we haven't finished learning about it today. So there we go. So now if we repeat it, here's what's going to happen. Let's look at our picture. We're going to find another point. So I'm going to use a cyan as my next color here. So we'll find the next point. So we'll take this. This is our guess 1, right? We're going to take that point on the graph, and we're going to do a tangent line at that point. So let's see, that should look something like that, right? And then the x-intercept of that tangent line, I think I drew that a little bit off. Let's draw that slightly better. There we go. The x-intercept of that tangent line is going to be our next guess. And as you can see, that's extremely close. That's going to be G2, that x value. It's still not exactly correct because the difference between here and here is, you know, that's a difference. It's not the same, but it's going to be much better, right? And so we would do that. So let's do it real quick. We can compute that. Redoing number 2 here. To make everything a bit smaller. Oopsie daisy. Actually, let's do it with just this side. Okay, all that a bit smaller. So going back and like redoing number 2, but with the new guess value, we have to evaluate f prime of our next guess 1. So we're going to do e to the power -1 minus 2 times -1. That's going to be 2 plus 1 over e. And then we're also going to need f of -1. So that's going to be e to the power -1 plus negative, or rather minus -1 squared. And we have 1 over e minus 1. Okay. So that was going back to our, let me put little boxes around these. Here's our f function. Oh, do a box. Here's our f function. There's our f prime function. Okay, so I was just plugging -1 into those two functions to get the slope and the y coordinate. Right. So now our L1, the linearization at guess 1, is going to be the y coordinate, 1 over e minus 1, and then plus the slope, 2 plus 1 over e, times x minus the x coordinate, which is x minus -1, is x plus 1, like that. Then we redo step 3, which is to set that equal to 0. And solve it. So I will move this stuff over. I'll subtract 1 over e, and I will add 1. So we'll have 1 minus 1 over e equals 2 plus 1 over e times x plus 1. I'll divide both sides by the 2 plus 1 over e. So we'll divide by 2 plus 1 over e, divide by 2 plus 1 over e. So that cancels out. Now I have x plus 1 on here. All I got to do is subtract 1 from both sides. And what I get is x is 1 minus 1 over e over 2 plus 1 over e, and then minus 1. What does that equal to? Let's approximate that. I'm just going to plug that into a calculator, see what that equals. Fraction 1 minus 1 over e over 2 plus 1 over e, and then minus 1. Negative 0.733. That's about what that equals. And that would be our next guess. So we'll say G2 equals that. Now, hypothetically, we can take that and we can go back to step 2 again and repeat the loop. Now, in my picture, that's going to be kind of hard to draw because I'll have to zoom in. And what I'll have to do is say, here is the point on the graph, and then I will make a tangent line at that point, which is going to be something like that, maybe. And then my next guess is very close. I mean, like, you can barely tell the difference between these lines because my resolution isn't very good, but my next guess is super close right here. Okay. And so if I were to do it again, I think I would get an even more accurate approximation. What you get from Newton's method is then a sequence of these guesses, right? And your initial guess, despite how it could have been really bad, leads to a new guess, which is better. And then the next guess after that is even better. And the sequence approaches the solution to the equation, which is the 0 of the function. Okay. And you could just hypothetically keep going forever. So this loop could go infinitely, but if you did that, then, well, I mean, like, a computer can't do that, right? A computer can't run a loop forever. So you just have to decide, like, how many times are you going to run the loop? How accurate do you need this to be? And so eventually you decide that's good enough and you stop, and then you have an approximation. That is how, I mean, maybe not Newton's method exactly, but some sort of numerical method similar to Newton's method. That is how Desmos is actually obtaining the negative 0.703 that we're seeing right here. Okay, it comes from some sort of method, probably using calculus in some way or other. Like, as you can see, this Newton's method involves tangent lines, so it does require derivatives. There's calculus involved, okay? But it's not the same as solving an equation with algebra. It's solving an equation, or it's quote, solving an equation, right? Because you never actually get, like, the solution. You just get better and better approximations of it. But you're solving an equation using calculus and a looping algorithm. It's pretty cool, right? It's a whole different perspective on solving equations that is totally different than the way you do it before. What's up? Oh, sorry, I heard someone come on mic and I thought, did somebody have a comment? That would be great. Love comments. Okay. Well, tell you what, I am going to show you guys. Oh, hang on a second. Oh, I gotta log in first. Let me log in. Sign in with Google. Oops. Sorry. Here we go. Here we go. Okay, so I'm logged in, and now I can show you like a better visualization of this. Here we go. We're going to do e to the x minus x squared again. There we go. And let's set our initial guess equal to 0. I guess, yeah, I'll do 0. Negative 2 to 2. Okay, zoom in. So here's our initial guess. I'm going to go down here and I'm going to kind of turn off colored lines and things. And so you can see, we'll kind of turn it back on slowly so you can see what it looks like. Okay, yeah, so you start here. With your initial guess, x1, or I guessed it guess 0. Sorry, I labeled it G0 earlier because I was like initial guess should be like the 0th guess. But here in this one, I built this a couple years ago and I labeled it x1. That's fine. Just a slightly different labeling scheme. Our initial guess here is labeled x1, and so there's our first point. The idea is you compute the tangent line, the linearization. That's our L1 that's here. Here's the formula for the linearization, and it's using the function and the function's derivative here, okay? And then you compute this point over here, which is where it crosses the x-axis. There, that point is now plotted and labeled x2, okay? Then you repeat. So find the point on that on the graph, find the next linearization, find its x-intercept, and plot that point. That's your x3. So there's the x3. That's the one we computed earlier. That was, as you can see right here, negative 0.733. That's what we did earlier, right? And then if we were to repeat the process, the next approximation you would get from this method is negative 7.038, blah, 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 blah. And we can zoom in on it here and see it. If we repeat it again, there's the next one, x5, and x5 is very close to the right answer. I have to zoom in really far before I can see that it is different. x5 is this number. Okay, so it's nice because it like kind of, it gets close to the right answer in just a small number of steps. Okay, and if I zoom way back out again, we can see where we started. Okay, if I change this initial guess, it changes how the sequence goes. Okay, so changing this initial guess, as you can see, sort of changes where this sequence, it starts further away and then it kind of gets closer. If I bring my initial guess much closer, like if I bring it really close, then now my sequence of points, now it's, wow, it's like really accurate. In fact, I might not even be able to zoom in far enough to tell the difference between, yeah, that's as far as I can go. I can't even tell the difference between x5 and the correct solution. They are technically different from each other, but they're so close that Desmos can't even zoom in far enough to see the difference. Okay. So, okay. Now, there's something you can see here. There's a formula that keeps popping up in my work here. You can see it says A5 is A4 minus F of A4 over F prime of A4. Previously, we had A4 was A3 minus F of A3 over F prime of A3. A3 was A2 minus F of A2 over F prime of A2. It's the same sort of pattern, the same sort of formula that keeps coming up over and over and over again, right? What's going on there? What is that? Well, the answer is that is taking, that's basically what you would get is if you take this process, step 3, where we take the linearization, we set it equal to 0, and we solve it to get the next guess. If we come up with a sort of a shortcut for doing that, okay, because you don't, it's kind of silly to take each like literal function that you get and set it equal to 0 and solve it. Like I'm doing that by hand, but it's really, if you're gonna program it into a computer, you can't just tell the computer to do it by hand, right? Like you need to come up with a more like general approach. So what I actually want to do is take that step, put it in generality, which means remove the specific information about what the guess value was, and even remove the information about what function we're working with. If I make it super abstract, then I can still solve the equation. And what I will get is a general formula for the next guess based on the first guess. Okay, so that's what I'm going to show you how to do next. This gets to one of the most important things you can learn from a math class. And from that, I am like totally serious. I believe that one of the most important things you can learn from mathematics is the value of abstraction. Okay, especially when it comes to problem solving. If science is about data and evidence, math is about abstraction and logic. Okay, and so science deals with like concrete information and building up evidence. Math deals with abstract information and like formal, rigorous logic. They're totally different. But this is one of the most important things you can learn, is the idea that if you remove some specific information, let's say that we have a function we just want to solve f of x equals 0. We're not even going to specify what that is. We have our initial guess, which we'll call guess 0 or x0. I was calling it x earlier, so let's go with x0. All you need to do is say, all right, my linearization at x0 looks like this. It's going to be f of x0 minus f prime of x0 times x minus x0. Okay, and even, instead of, we can make this even more general. We've generalized the function without specifying what that is. We're generalizing the guess without specifying what that is. And also, we're not even going to necessarily talk about the initial guess. We're just going to talk about the nth guess, which means like some guess down the line. We're going to represent that as xn. Like that. Okay, so we're not even specifically talking about the first step in the process. We're just talking about a step in the process, some step in the process, because all the steps look the same, right? They're all take the guess, find the tangent line, find the x coordinate of the tangent line, the x-intercept, and set that equal to the next guess, right? So we've abstracted this out as far as we can at this point, and now all we need to do is set this equal to 0. and we need to solve for this x value. Let's do it. Well, I could add this whole term to both sides, right? So I could move that over here. So we've got f prime of x0 times x minus x, sorry, f prime of xn. I wrote the wrong thing again. X minus xn equals f of xn. We'll divide by the f prime to cancel that out. F prime of xn, divide by that, that's gone. And then we will add xn to both sides. And we get x equals the xn plus f of xn over f prime of xn. And I just realized I did the wrong, I messed up. I just realized I messed up. Okay, I had to go back and fix a mistake. I don't know why I put minus here. That's not minus, that's supposed to be plus. I'll fix my mistake in green here, dark green. That's supposed to be plus. So that was plus. I don't know why I put minus. So what that means is there's a minus. Instead of adding it to both sides, we subtract it from both sides. So there's a minus here, so we divide by a minus there. And then this ends up being a minus right here. There we go. That was meant to be a minus. Sorry about that. And there we go. So that is a general formula for finding the n plus first guess value based on the nth guess value for an arbitrary function f. So now the algorithm just looks like this. Algorithm to approximate the, or a, 0 of f of x. It looks like this. 1, make initial guess. x0 equals blank. Plug that in. 2, calculate next guess. x1 equals x0. This is going to be your next number in the guess. This is the next guess. So I'm going to label that xn plus 1, which is the next, because if this is n plus 1, which is the next one after it. So x1 would be x0 minus f of x0 over f prime of x0. 3, repeat. x2 equals x1 minus f of x1 over f prime of x1. x3 would be x2 minus f of x2 over f prime of x2. And in general, just use that. The n plus first number is the nth number minus f of that divided by f prime of that. So as many times as you want until you reach the desired level of accuracy. Okay. So this is a nice simplified version of that algorithm. It all comes from the tangent lines and find the point and then make the next tangent line and find the point. It all comes from that. But when you actually implement it, it's just one formula that you repeat over and over and over and over. So that's pretty sweet. Let's look at what that would be like. See what that would look like. So I'll bring this guy back here. Let's see. Let's open a new one. you set f of x equals something. I will stick with the same function for now, but we'll change this function in a moment. We're going to define a new function called n of x, and n of x is going to be x minus fraction f of x, over f prime of x. Okay, that's a function. So I can ignore that function for now. But what I want to do is I want to say, let's make an initial guess, x a, I guess I could call it x0, have that x0 equal whatever our initial guess is. Okay, and then we're going to do n of x0. Hey, remember how the second guess was -1? And that was like this whole calculation? All we needed to do is plug x0 into, we don't even need this. We could just put the 0 right in here. N of 0. That's your first guess. If you want to know what the second guess is going to be, do n of 0. So do a nested, like take the output of that function and plug it back into the same function. There's the next guess. Does that number look familiar? -0.733. Do another one, n of 0, -0.7038. That was the next number we got, right? So this now becomes, you can literally just do this as many times as you want, and this is equivalent to applying Newton's method over and over and over to get successively better and better and better approximations. And that's what it looks like. It's just, this is actually, I think this counts as a recursion rule or a recursive algorithm in a way, because the output is being plugged back in. So it basically is this long composition of a function with itself over and over and over again. Kind of cool. So that's quite easy to implement in code and on a calculator and stuff. And now we can change this function to something else. Say we want to know, say we do like x cubed plus 3 or minus 3. Okay, so here, this number is going to be the like cube root of something. It's going to be the cube root of 3, that number. Currently, this says undefined. And the reason this says undefined right now is because the initial guess is 0. With an initial guess of 0, the first tangent line is going to be horizontal. And let's go back to the original. This doesn't work because with a horizontal tangent line at that 0 point, it's never going to hit the x-axis. So that guess just doesn't work. But if we try a different guess like 1, then now we have something. And now if we improve this by doing a few more iterations, let's iterate that 4 times. There's four iterations of Newton's method, gives us 1.44225. The answer should be the cube root of 3, which indeed is 1.44225. In fact, these agree with each other all the way out to the 4,9. And then that 7,896 is different. It's a 57031 or whatever. So yeah, there's lots of different things you can use this with. Okay, so it's great for solving equations. You folks have any questions so far?
So how do we know when to stop looping through?
Good question. Let's look at some successive guesses. Right? So there's 1, got 1, n of 1, n of n of 1, n of n of n of 1, n of n of n of n of 1. And what we can do is look at the difference between these values. So from 1 to 1.6 repeated, that's like a pretty big jump. 1.6 repeated to 1.471 repeated is also, you know, pretty significant. Now we've jumped to 1.4428. Sorry, yeah, and then 1.4422 something. And what we're seeing is that these numbers are getting closer together if at each stage you compute the difference between successive guesses. When that difference gets small, but basically the difference between the successive guesses is an approximation of the error in your guess. So if as that difference gets smaller, that gives you a measure of like how close you are. Like we can say that since these numbers are now starting to repeat themselves out to the 1, 2, 3, 4, 5, 6th decimal place, we can say that this approximation is accurate to 6 decimal places because the error is less than that. Does that make sense? The difference between these guesses doesn't appear until the 7th decimal place. That make sense?
A little bit, yeah.
Okay. If you want to say you want to be accurate to like 8 decimal places, the way to do that is to continue the process until you see repetition out to 8 decimal places. So 44224957, 44224957. There we go. So we're now seeing repetition all the way out to 8 decimal places. In fact, beyond 9, 10, 11, we're seeing repetition out to 11 decimal places. So at this point, right at this stage here, we can say, because we see that repetition, this is accurate up to that number of decimal places. So those are like locked in. And it might be wrong after that, but it's at least correct up to the 11 decimal places we're seeing on screen.
And on assignments and quizzes, will it specify how many decimal places you want it accurate to?
Yes, it would. Although, funny you should ask that, but the timing of our assignments and things has turned out that we're probably not going to see this topic show up on a quiz or an exercise set. It might show up on the next exercise set, I guess, but then it would be a little out of place because most of that exercise set is going to be focused on chapter 5. So I don't know. I don't think I'm going to bother putting it on there. But if instead of thinking about it from a school perspective of like, how do we know what to do as a student to get the right answer, just think about it from an engineer's perspective. How accurate do you need your approximation to be? I mean, it kind of depends on what you're using it for and the sensitivity of your project. I mean, if it's a shed you're building in your backyard, then probably not very accurate. But if it's like a lunar module or like, a rover that's going to Mars, then like there's a high stakes and you want it to be super freaking accurate, right? So like, yeah, it just depends. I don't know how engineers determine that sort of thing. That's not really my area. I just leave it up to you guys as the engineers and the computer programmers or whatever to like determine that through your work or through your experience or something, or by, I don't know. That's not my job. Yeah, so that's it for today, folks. We will tomorrow we'll have some fun with Python. Like I said, you don't have to have any background knowledge in how to do things with Python. I will show you how to do it. You don't need to download anything. We're just going to use an online Python environment that's entirely web hosted. So yeah, I'll just kind of walk you through it. And don't let me forget, I also want to explain to you tomorrow why, of all the possible numerical methods, Newton's method is actually one of the worst. So sorry to break it to you, but it's one of the easiest to introduce at this level that you guys are at, but it also sucks. So I'll show you why tomorrow. Bye, everybody.